Hello and welcome to MT3. We are still on Fourier expansion, so this is the second part in the series on Fourier expansions, and we stopped the first part over here. Here we are, where we had posed three questions about our Fourier series. We had developed a Fourier series, a complex Fourier series for the period 0 to 2 pi, and we asked the question, what if you could, how do we generalize this to another period from x0 to x0 plus L? The second question was, when dealing with real functions, we saw that this complex basis set led to sines, and we didn't see about the cosines, but it does lead to sines and cosines. So how can this be done generally? And finally, for general functions which are not periodic but are defined in a finite interval, can we still use a Fourier series for these kinds of functions? And the answer to all of these is yes, it can be done. So let's have a look at the period change first. If you use a period x0 to x0 plus L, that means the function is periodic with period L, and our starting point is x0. Well, this is clearly more general, and this would cover any function in one dimension. I'd like you to show that the procedure we have used to derive the exponential functions in the previous recording, and you can have a look at these notes when you have them in front of you, that procedure leads to functions of the form phi n of x, which is 1 over the square root of L, so the period enters there, times the exponential of I times 2 pi n x over L. Now just to check, if I put x0 to 0, and x0 really doesn't matter, but if I set L to 2 pi, which is what we had earlier, then we get 1 over the square root of 2 pi, the exponential of the 2 pi cancels off with the 2 pi in the L, so you have the exponential of I n x, which is exactly the basis function we had in our earlier part. Let me just remind you of where that is. These are the basis functions we had earlier, and if you set the period to be, L to be 2 pi, then you recover these basis functions once again. Okay, so let's go back. And I've provided a hint here as to how do you actually show this. The boundary conditions are now y of x0 is equal to y of x0 plus L, and likewise on the derivative of y. So apply the first set of boundary conditions to phi of x is equal to a e to the I lambda x, which is what we had earlier, and show that lambda is now 2 pi n over L. Earlier we had lambda was just equal to n. Then you normalize these functions and show that they are equal to the functions I've shown here. Okay, so that's an exercise for you. The second question is, what happens to real functions? And how do we... So what we had, just to remind you, what we had seen for this square wave example is that for real functions, we could combine these basis functions in pairs to get, in this particular case, it was sine of x, sine of 3x, etc. So we had an expansion which then was manifestly real. The question is, can it be done more generally? And the answer is yes, and this is how it proceeds. So if f of x is a real function, then f of x is equal to f star of x. That is, it's equal to its complex conjugate. Well, let's put down the Fourier expansions for f and f star. The Fourier expansion for f is the sum n goes from minus infinity to infinity cn e to the I n x over the square root of 2 pi. And that's equal to the Fourier expansion for f star of x, and just take the complex conjugate of this, so you'll get cn star e to the minus I n x over the square root of 2 pi. Now I'm going to assert, and I'm going to show you why, that this sum here is equal to the sum from minus infinity to infinity c of minus n star. So instead of n, now we've got a minus n there, e to the I n x. The minus n is gone from here and divided by the square root of 2 pi. Because if that's true, then if you compare this sum here with this one here, you should be able to see that the Cn is equal to C star of minus n for all n. But how is that the case? How is this done? Well, the first step is, in this second sum here, let m equal to minus n. Can you do that? Sure. Why? Because n is a dummy index. I'm summing over all the n's. So whatever you call n doesn't matter. I could call it k, p, q, z, whatever you want. Just don't call it x because there's an x there, or an I because there's an I there. We're going to set m to minus n. So I'm changing variables in a way. Then the series kind of inverts itself. M goes from infinity to minus infinity. C of n star becomes C of minus m star. And your exponential becomes e to the plus I mx divided by the square root of 2 pi. Now, if this was a convergence series, then the order of the sum does not matter. So we observe that. Now, I have assumed that these are convergence series. So we can reverse the sum. Instead of m going from infinity to minus infinity, we go from minus infinity to infinity. Everything else stays the same. Now, m is a dummy index. It is summed over. So I'm going to call m n. And that's how we get this term over here. Okay. Oh, good. Now we are getting there. Now let's take these 1 over the square root of 2 pi's, which are going to be in the expansion side, and I'm going to multiply f of x by the square root of 2 pi, and that then gives us, so that expansion is now written as c naught plus, this is the sum over positive n, and then we have the sum over negative n. That's just a rearrangement of the Fourier series so far. Next, we let, in the second sum over negative n, we let m equal to minus n. Why not? Sure, we can do it. This is a dummy index. And using simple manipulations, or once again reordering the sum, what we can show very nicely is that you can write this second sum as the sum n goes from 1 to infinity, like the first sum, c of minus n instead of c of n, e to the minus I nx instead of e to the I nx. Now, if you are unsure as to what's happening here, write down the first few elements of this sum and this sum explicitly, and you will see what is happening. Now we are able to combine these two sums. So we have a cn, c of minus n, cn, c of minus n, e to the I nx, e to the minus I nx. But the second c of minus n, the c of minus n, is just cn star. We proved that above. And e to the I nx is the cosine of nx plus I sine nx. E to the minus I nx is the cosine of nx minus I sine nx. Put that in there. And now we combine terms. There's the cosine term and the sine term, which is now made evident to us. So this Fourier expansion becomes c naught plus the sum n goes from 1 to infinity of cn plus cn star, that's a new coefficient, times the cosine of nx, plus sum n goes from 1 to infinity of I cn minus cn star sine nx. Okay, now we're going to make one definition. It's just to get rid of the 1 over square root of 2 pi's. I'm going to define dn is equal to cn divided by the square root of 2 pi. And this lets me write f of x is equal to d naught plus exactly what we had before, but now we have d's instead of c's. Okay, it's nearly there now. Next, we're going to define an is dn plus dn star, and bn is I dn minus dn star. Show that both an and bn are real for all n. Also that d naught is a naught divided by 2. This is something, it's quite simple, just show it. And so now we've got real coefficients. These are the an's. This whole thing here is the bn, and this is a naught over 2. And therefore we write down our Fourier expansion for a real function f of x as a naught over 2 plus the sum n goes from 1 to infinity of an cos n of x plus bn sin n of x. And this is the Fourier series that you will have learned when you first came across it. In fact, this is the way Riley, Hobson and Benz begins their exposition on Fourier series. Now, I hope I will convince you soon that the complex expansion is far neater. Alright, but so far this looks fine. And I said this is the standard form of the Fourier series for a real periodic function in the interval 0 to 2 pi. Now the question is, how do you find these a_n's and b_n's? Well, let's remember a_n is dn plus dn star, which is 1 over the square root of 2 pi cn plus cn star. And we know that the cn is given by the inner product of phi n hat with f, which is this integral, with the weight function being 1. I've not said it anymore, but we are going to have the weight function as 1 in all of our norms in this particular part on Fourier series. So the weight function is 1 by choice, and therefore Cn star is simply the complex conjugate of this integral. I've written it down here, and that allows us to write down an. An is 1 over pi of the integral. Remember, it's the sum, and when you add these two exponentials together you get a cosine. So an is 1 over pi, the integral 0 to 2 pi of cos nx f of x dx. Nice and neat. I mean, I love this. You're getting something now. This is I hope this is starting to remind you of what you have seen about Fourier series before. Similarly, show that bn is given by 1 over pi, the integral of 0 to 2 pi sine nx f of x dx. And so now we have our real Fourier series. It's given by what we had, this expansion over here, and we also know what the coefficients an and bn are given by. That's great. Now, what about generalization of all of this stuff to functions that are periodic, to real functions that are periodic in x0 plus x0 plus L? Well, this can be shown, and you can try it out on your own, or, well, look at Riley's book. In fact, there are many ways to show this. You can show that f of x is now given by a0 over 2. We have the sum, n goes from 1 to infinity, an. Instead of a cos nx, we now have cos 2 pi nx over L. Instead of a sine nx, we have sine of 2 pi nx over L. This should not be a surprise, because it follows directly from the way in which these functions, the exponentials, were generalized from an exponential of I nx to an exponential of I 2 pi nx over L. And that's simply a consequence of that generalization. Okay, and our coefficients now are given by, there's a small change here. Instead of a 1 over pi times cos nx fx, we now have a 2 over L. Remember, 1 over pi is 1 over half the period. And likewise, 2 over L is 1 over L over 2, which is 1 over half the period. So it's consistent. So the an is given by 1 over half the period, that's 2 over L, of the integral x0 to x0 plus L, of the cosine of 2 pi nx over L, that's this term here, f of x dx, and bn is likewise given by a similar kind of integral, but with a sine in it. Now you can show these, that these two coefficients arise by using the orthogonality relations, which I never remember. So I prefer working with the complex Fourier series for exactly this reason. You can show that if you had these orthogonality relations worked out, that means the integral over this period of sine of 2 pi nx over L times cosine of 2 pi mx over L dx is equal to 0 for all mn, and then you have these two here, then you can use those orthogonality relations, and I really encourage you to do that. And if you use them together with this Fourier expansion, you will show that an is given by this and bn is given by this. Please do that, because it's nice to know how to handle these kinds of proofs. Now I put a note here. complex expansion is so much more elegant. We don't have any of these complicated integrals. It's all easy and really elegant. You can write down the complex expansion in 2 lines. The real one takes more effort. Okay, so what about non-periodic functions in a finite interval? I've given you an example here. This is the function f of x is equal to x squared in the interval minus pi to pi. Now just to remind you, so this is the interval minus pi to pi, so x naught would be the starting point, it would be minus pi, and the period L would be the period of this, the length of this interval, which is 2 pi. So if you put x naught is equal to minus pi and L is equal to 2 pi, then you get this then x naught to x naught plus L gives you this period. Okay, so this is our function. Now it's not periodic, but what we can always do is make it periodic. I can just say I'm going to add include periodic images of this function all over the place. So I made these periodic images of f of x. Now I have something that is periodic. Now you don't care what my Fourier expansion is going to do outside of this of minus pi to pi. So it doesn't matter if you made this thing periodic. I mean, it works. As long as the expansion is valid in minus pi to pi, what happens outside is immaterial. But if you make this function periodic, then we can use the Fourier series. So now we make some observations. F of x, which is x squared, is even in a symmetric range, minus pi to pi. It's an even function in a symmetric range. This range is symmetric about the origin. Therefore, all integrals of the form minus pi to pi f of x gx dx will be 0 if gx is an odd function. Therefore, these bn's, which are defined to be from minus pi to pi, f of x sine 2 pi nx over L dx, this will be 0 for all n, because the sine function is odd with respect to the origin, and f of x equal to x squared is even, and this integration range is in symmetric range about the origin. So only the cosine terms will remain in this Fourier expansion. And if you can make use of symmetry in this way, you can simplify your life considerably. So f of x, which is equal to x squared, will be a naught over 2 plus the sum n goes from 1 to infinity of a n cos 2 pi nx over L, where L is equal to 2 pi. So that gives us a naught over 2 plus the sum a n cos nx. All right. And we know that these coefficients are going to be given by our formula, which we had on the previous page. We get a 1 over pi, the integral minus pi to pi x squared cos nx dx. Now it's a matter of evaluating these coefficients. Quite often for n is equal to 0, you have to do it specially. So for n is equal to 0, we have a naught is 1 over pi, the integral minus pi to pi of x squared dx. That gives you 2 pi squared over 3. And for n greater than 0, we have a n is equal to 1 over pi, the integral minus pi to pi, x squared cos nx dx. Now you got to use integration by parts twice. I've just provided a little hint here as to what you need to do. And if you use that twice, it's easy to show that what you get is minus 1 to the n 4 over n squared as being equal to a n. This lets you write the Fourier expansion for x squared in this interval as pi squared over 3 plus 4 and times the sum minus 1 to the n over n squared cos nx. And this is where you can stop now. That's the Fourier expansion for x squared. And if you wanted to see if it's equal to x squared, go ahead and graph this using Python or gnuplot or whatever you want. It's kind of fun to see what happens. There's a nice result. If you put x is equal to 0, and you have a 0 here, and the cosines are all 1, what you have then is that pi squared over 12 is equal to plus the sum n goes from 1 to infinity of minus 1 to the n plus 1 divided by n squared, which is 1 minus a quarter plus 1/9 minus 1/16 plus 1/25. I think this is just cool. I mean, 3 blue, 1 brown, he has at least one video on how a series like this, I don't know if it is this one itself, ends up giving you something which is proportional to pi, or pi squared in this case. And he has a geometric reason for showing you how this can happen. I mean, have a look at one of those videos. It's absolutely fun watching it. But this is one way of getting an expansion for some power of pi in terms of an infinite series. And in fact, yeah, you can find many more such from a Fourier expansion. Now here's a question for you. Given this expansion for x squared, can you find the expansion for x cubed in the same interval? And I've given you a hint. It should take you approximately 1 minute to do that. So what would you do to take this expansion for x squared and create an expansion for x cubed in the same interval? What would you do that would take you approximately 1 minute? It's a challenge. Have a go at it. You'll find the answer in Riley, Hobson and Benz, but try not to look. All right, here's another challenge. If f is non-periodic, is the Fourier expansion unique? Here's an make it more specific. Find 2 Fourier expansions for the function f of x is equal to 1 in the range pi to 2 pi. And giving you a hint, this can be very, very simple. Further hint, one of these expansions is in these lecture notes. Have a go at it. And if you can't figure it out, we'll discuss this in the tutorial. Now here's something. When making a function periodic, try to avoid discontinuities. Discontinuities always cause the Fourier series to converge more slowly, and you'll have artifacts. These artifacts go by the names of the Gibbs phenomenon, and if you look at an advanced text on Fourier series, they'll mention what this is. So if you've got a function f of x is equal to x in the range 0 to L, well, you could make it periodic by simply translating this function as shown here, but then you have a discontinuity at 0, at L, at 2L, etc. Or you could do the following. You could make it a zigzag function. So here's this function, and then you double its period, but you don't care about the part from L to 2L, so frankly it doesn't matter. But now this function is continuous, and this would lead to a better behaved Fourier expansion because there's no discontinuity in the function itself. Now there is a discontinuity in the derivative that causes a problem, but it's a lesser problem than this one here. All right, so I'm going to end with one theorem and just say a little bit about it. Parseval's theorem. You'll find this discussed in the last section in Riley, Hobson and Benz in chapter 12. That's 12.8. But they have a slightly long-winded proof which can be made much simpler if you stick with the complex Fourier expansion. So let's go back to our complex Fourier expansion. F of x is equal to the sum Cn phi n hat of x. And remember, the phi n hats are given by this complex e to the I nx. And this is for x in the range 0 to 2 pi. Now consider the inner product of f with itself. So the inner product of f with itself is the inner product of f with this infinite sum. Once again, if the sum is convergent, we can pull it out of the inner product, and we are left with the sum of Cn, the inner product of f with phi n. Now I'd like you to show this. This is easy, but please show it. The inner product of f with phi n is equal to Cn star. So here we have a Cn. This is now the complex conjugate. Okay, and that means the inner product of f with itself is the sum of the modulus squared of the coefficients of the expansion. The inner product of f with itself is the integral from 0 to 2 pi of the modulus of f of x squared dx, and that's just equal to the sum of these mods squared of these coefficients, and that's Parseval's theorem. Now I'm not going to say anything more about it, but for real functions, here's the proof. For real functions, you can show that this leads to a slightly more complicated form of Parseval's theorem, which is shown down here. And for functions in the periodic in the interval x0 to x0 plus L, these become, this whole thing becomes, so the complex form of Parseval's theorem stays the same as before, but the real form gets factors of L over 4 and L over 2 in it. As I said, once again, the expressions for the complex case remain simple, but those for the real case are a little more complicated. All right, so this form is given in Riley, Hobson, and Benz. Have a look at it. All right, I'm going to end here with just one note, is that Riley, Hobson, and Benz use a complex expansion with different normalization. So they're CR. So when you read that book, the coefficients CR are equivalent to RDRs. And finally, there's one more note here. There's an example of an application of Parseval's theorem in section 12.8. So please have a look at that. So with that, we have covered our kind of excursus on Fourier expansions. Let's just summarize. We started off with this operator L. We showed that it's Hermitian in this interval under periodic boundary conditions. Actually, this was an exercise for you, so please make sure you've done it. We then found the eigenfunctions of this operator L. Those were the complex exponentials. We then used the fact that these eigenfunctions are the eigenfunctions of a Hermitian operator, so they form a complete basis set that let us expand any function f of x in terms of the basis set. Everything else after that is just a variation on that expansion. We have generalized the expansion to be applicable to functions that are periodic in the range x0 to x0 plus L. We have generalized it to special case when the functions are real, when the functions are not periodic but are defined in a finite range, and we've come across Parseval's theorem. So I'll stop here. To find out more about this topic, look at either the book by Arfkin, I forget which chapter, or the book by Riley, Hobson, and Benz, chapter 12. Thank you for watching.